And we can start the talk. It's my great pleasure to have today Tibor Szabó from Freie University of Berlin. And he will talk about new Ramsey multiplicity bounds and search heuristics. Please, Tibor.
Thank you very much. Thank you, Benny, for this invitation and the opportunity to present our results with my colleagues in Berlin. So, as Benny said, I will talk about a combinatorial problem, very old combinatorial problem, a couple of them which go back to questions of Erdős in the 60s. We study these questions, and as you will see, we will prove new results using computer-assisted proofs. So this is gonna be, in a large part, a talk which or a direction where I haven't been giving a talk. Many of the parts in this talk will be experimental research, and this is my first serious attempt at that. And of course, my colleagues, Olaf Parchik is at the FU Berlin, and Sebastian Pokuta and Christoph Spiegel work next to us in the Zuse Institute Berlin. So let's see what are the problems. As I promised, we will go back a few decades. So the starting point is Ramsey theorem. And all of you hopefully know that for every t, there is some smallest number, finite number, r of t, the Ramsey number, such that any two-edge coloring of the complete graph contains a monochromatic clique of that size. So maybe I'm going to point here. Right, let me close this on my screen. Got it. Yeah, now, good. That's right. So what is known about it, not so much. Two exact values for 3 and 4. For 5, you already don't know. And the bounds on the Ramsey number in general are exponential, but the base are very far from each other, even after this extremely exciting, hopeful advance that the upper bound is now, which was standing at 4 to the k for almost 100 years, it appears to have been reduced by 1/1000. So whenever I teach Ramsey theorem, this is what I'm always telling, that these two bounds, the square root 2 to the k and the 4 to the k, are unmovable. They stand there for 100 years, and now I can revise my teachings, maybe. Okay, so what is the Ramsey multiplicity problem? The Ramsey multiplicity problem starts with Ramsey theorem. We know that if we are passing the Ramsey number threshold, so the R of t, we will have a monochromatic KT. The question is that for a given n, how many monochromatic KT will appear necessarily in any two-edge coloring of Kn? Well, I know that if n is at least a Ramsey number, that this is at least 1. In fact, it's at least 2. But in general, for any n, the starting point is the result of Goodman, who dealt with the case when I'm looking for monochromatic triangles. And he proved the perfect theorem. He just, for every single n, determined the exact number which you can guarantee. And this is a bit complicated, but if you substitute, you will see that this is always asymptotically number of vertices cubed over 24, which means that roughly 1/4 of the triples will be monochromatic. and that I give you some nice human proof also in this lecture. I will include here this lovely double counting argument to show it. So we have this stroke of genius that, okay, let us double count an object. What is that object? The number of K12s, the red K12s in some two-colored G. I imagine, by the way, I will imagine that the graph G is having the red edges and its complement is having the blue edges. Oh, where are we? Okay, so these are the red. So I'm going to double count the K12s, red K12s and blue K12s. On the one hand, red K12s are nothing else but for every vertex, I have a degree neighbors, and any two of them is determining for me a K12, and I sum it up for all vertices. Similarly, for the blue ones, the complement, any non-edge pair of non-edges will create me a blue K12. Now I can count this from the other side. K12s can be partitioned in two classes, the ones which complete a red triangle and the ones which complete a blue triangle, the red K12s. And this way I count essentially triangles, namely this triangle pattern appears exactly this many times, but this triangle pattern here appears, only 1/3 of that time. Namely, here, if you see here, this vertex is really special. This is the vertex of the K12, the degree 2 vertex of the K12, and here these vertexes are not special. So that's why I'm counting here this 3 times the number of red triangles. And at the end, I'm interested in the number of red triangles. The same for the blue one. So here, this sum is just 3 times the number of blue triangles plus the triangles with 2 blue edges and 1 red. Now, here on the left-hand side, I can use convexity to do bound this sum of 2 and x choose 2s. I bound it. These things sum up always to n-1, so this is altogether n-1 times n. Divide, express, and on the left-hand side, I find myself having, I think, this number. And on the right-hand side, if I rearrange this sum, I will find all the triangle patterns together. This is giving me n choose 3, right? Because these are all possible triangle patterns. And then I have 2 times the quantity I'm interested in, and that's why I did the whole thing. So here I have the quantity I'm interested in, I express it, and I get what I wanted. Very nice. At the beginning, we just had to say, what are we double counting? And we proved Goodman's theorem. I would like to ask you to please tell me, interrupt me freely if you have any questions.
Or maybe if you want, you can also write in chat. I'm following the chat, so if people will write.
Okay, that's also fine. So Benny can tell me if there is some question. Goodman immediately asked the question, what about when t is at least 4? And Erdős immediately jumped on this question a couple of years later and gave at the time a very new, using a very new technique, the probabilistic method, to give an upper bound on the number of KTs and or red KTs and blue KTs in a coloring of a complete graph, or as we will talk about it all the time, the number of kts in G and the number of independent sets of size T in G. And I will try to consistently color kts with red and independent set with blue, so we remember the coloring. And if you calculate what's the expected number of these structures in the random graph, in the uniform random graph, you will find that roughly 2 to the exactly the expectation is 2 over 2 to the t choose 2 factor of all t tuples. Right? So every pattern among the t choose 2 to the t choose 2 edges can take any pattern, and 2 of them provide me monochromatic. This is the fraction I will see. So it means that there exists such a graph, and that means that this number will never and randomness in the proof of construction for the Ramsey number is our best tool. I expect that these colorings, which will minimize red and blue kts, has to be somewhat fair to the 2 colors. It's a reasonable assumption, and conjectured that this random upper bound here about the density of the structures, the kts and the independent set, is what is given by the random. So 1 over 2 to the t choose 2 minus 1. And so the formal definition of CT is just that it's the limit of the minimum number of kts and number of independent sets of size t in a graph G divided by the factor n choose t. And it's a easy exercise to show that in fact this limit exists because the sequence increases. And another motivation for this conjecture is, of course, that it is, first of all, trivially true for t equals 2 when this number is simply 1, right? So in any graph, number of k2s or number of independent sets of size 2 is every edge, every pair. And Goodman's theorem does give us 1 over 4, which is, in other ways, exactly what it needs to be. But for t at least 4, it was not clear how to prove it or what to do. For many years, people tried to show this conjecture, and this looked really a reasonable conjecture. Giraud gave a lower bound, which was at least some constant, 1 over 46, but still far away from 1 over 32. And it took a great paradigm shift, which was achieved by Thomasson, who maybe needed to believe that this conjecture is actually false, and then construct his counterexample. So this happened in 1989, and his constructions were very much not random. The opposite what conventional intuition would suggest. So he took blow-ups of appropriate graphs, small graphs. Here you can see what is a blow-up. You just introduce m, the same number of vertices for each vertex of a small graph, and you create an independent set. And in between, you create complete bipartite graphs whenever you see an edge. So that's just a symmetric blow-up. And the ingenuity of Thomasson construction was how he chose his base graphs, which were very much not simple. They came from geometry, and I will say a bit more about them later. Here, I just put here this table, not for you to read it, but you can see that over the years, many people studied this problem, and the results on it were improved a little bit and sometimes a bit more. So just that you understand our notation, I introduced this letter ET, which is giving me the fraction, the comparison to the conjectured bound. So if the conjecture of Erdős would be true, so CT would be 1, then, no, CT would be the conjectured value, then ET would be 1. So any value which is less than 1 indicates that the conjecture is false. Right. So Thomasson, with his original construction, and immediately in his paper, he tweaked it and improved it, achieved, you can see 97%, 97.5% of the original bound, and also for 5. And the great thing about his construction was that it works for any t. So for any t, it gives a different graph, which then you can raise to this blow-up power. And that gave a counterexample for any t. Are there any questions? Good. You can see that the very first value, so maybe the first most interesting one, was studied further. A completely different construction was given, well, not completely, seemingly different construction was given by Frankel and Rödl, giving a slightly worse bound, also counterexample. And then Thomasson improved his own construction. So it's now below 97%. And more recently, Evans, Zohar, and Lineal reduced even more. But this is now only in the 4th digit. And you can see that, yeah, and then others improved further values. But the best bound, the general bound on ET is still the original construction of Thomasson with the neural analysis. On the lower bound front, the flag algebra technique of Razborov was very successful in this problem, and Giroud's lower bound was improved greatly. And the most recent one is from last year by Grezhik, Lee, Riditsky, and Volets, and this is now standing at a bit below 95%. So you can see that these bounds are reasonably close. What we do in our paper is we reduce further the upper bound for E4. So we improve, and in the abstract I wrote significantly. So here, this you have to take with a grain of salt. So in this business, what is significant? So we reduce it. This progress here, you can see, was pretty slow. It slowed down very much, and now we reduce it by some more than 20% of the gap, the full gap between the lower and the upper bound. So I would say in this business, this is a significant improvement. And we also gain a little bit on the E5 construction, which was standing also there since Thomasson's work. And I think we established the first flag algebra lower bound for the E5 problem. And our upper bounds are blow-ups of Cayley graphs, and just like Thomasson's, and just like actually everyone else's. And we found them through search heuristics, and I will talk a little bit about that. And the lower bound, yeah, it's flag algebra. Okay. Are there any questions about this problem? Good. So then I go on to the next problem of Erdős in the very same paper where this was raised, where the previous problem was studied. Erdős asked, what happens if I, in this problem of counting independent set, I reduce myself to graphs with a given clique number? Namely, I assume that graph G does not have a T-clique, and then I'm trying to count independent sets of size C, S in it. And this limit, which also exists, is called GST. Okay, so here are some trivialities about GST. The first thing is that obviously GTT is at least the previously found CT. It is just a very special case of it when I have no T-clique in my construction. Another simple upper bound on GST general is given by the Turan graph, right? So the Turan graph is just a blow up of the complete graph. We blow it up into T-1 equal sized independent sets. And if we calculate the number of, this has no T-clique, and we calculate. Yeah.
我靠！你是两个都吃了吗？还是吃哪个？
那个原来的西达摩我就没吃
I
了。
think they unmute. Okay,
Yeah.
I can continue. So the bound which you get from the Turan graph is 1 over T-1 to the S-1. And Erdős conjectured here that maybe there is equality, again, based on what is true, namely trivially when the minimum of S and T are 2, then I have that this conjecture is true. So the Turan graph does give the best bound. Right, so this is trivial because here essentially I forbid edges. So everything is an independent set. And G2T is just Turan's theorem, right? So I forbid the T cliques and I'm counting how many non-edges do I have, and that's the 1 over T minus fraction. And if we look, Goodman's theorem will give us the case when G3 is 3. When the two parameters both are 3, because 1 over 3 minus 1 to the 3 minus 1 is just 1 over 4. One of the examples for Goodman's theorem, tight examples, is the Turan graph. But it turns out that the Turan graph is not all there is. Nikiforov noticed that for the G4-3 problem, the blown up 4 cycle gives a better construction than the Turan graph, and actually showed that GST can only, so this conjecture can be sharp, the equality can be sharp only for finitely many pairs. Shagnik Das and et al. Actually proved that and among these all, I think Benny is there. Sorry for missing your name there. There are 5 authors, so I save it. The blown up 5 cycle is in fact tight for the G4-3 question. And on the other hand, the G3-4 question, the Turan graph is the tight one. So for this, the conjecture is true. Pikulko and Vaughan went further. They showed the truth of the conjecture for 3, 5, 3, 6, and 3, 7. So this is when we are counting independent sets of size 3, but gave counterexamples to the conjecture for 5, 3, 6, 3, and 7, 3. But not only that, even more, they were able to determine the exact value here, and they were each blown up of graphs. So 5, 3 is the blow up of the 5 cycle, the very same graph. But here, the blow up graph is something much bigger, the Clebsch graph, a 5 regular 16 vertex graph. So that's a kind of an amazing result that you can prove an exact theorem with such a large example. And for G44, they also have a nice construction, which is a blow up, but it's a weighted blow up, and they did not succeed in making it tight with their flag algebra lower bound.
Tibor, it's maybe good to say that all this is with flag algebras, right? Including
the lower bounds are all with flag algebras, and they also achieve stability of the structure. I will talk a little bit about that as well. But here, this is an interesting question, because here flag algebra suggests that this is a tight construction, this weighted blow up, but for whatever technical reason, it is not possible to, or they were not able, and it was not possible to make it a proof.
This is a weighted blow up of Turing graph, or
I don't remember. It's a simple graph. I think it's a Ramsey graph on 8 vertices.
Okay.
As you will see, because this is where we are heading, we look at the G45 case, and we succeed there to determine this extremal fraction, which comes from a 13 vertex graph, which happens to be the unique Ramsey graph for the asymmetric Ramsey problem, where you don't allow triangles and you don't allow blue K5s. So this is a maximal Ramsey graph for that, and the blow up of this gives the best construction, and you can show stability. And here you show a very strong form of stability. What does that mean? That any G, large enough G, where this is some constant, admits a strong homomorphism into this Ramsey graph, meaning it is a homomorphism into it which respects also the known edges. So it means that the graph really looks like a blow up of a subgraph of this. And any graph G admits such a thing. It cannot be true after changing at most that fraction of edges, whatever is the difference between its 4 independent set density minus the optimal one. So this is a constant depending on this number, and of course, in particular, it implies that if the GN, if the independent set density is equal to the optimum, then you are a blow up of this Ramsey graph. So our original motivation was to study the C4 problem, so the 4 Ramsey multiplicity, and try to understand that better. And as you could see, we did not, well, we succeeded. We improved the best upper bound by a lot, but we did not succeed in the sense that we still don't understand the main thing about the problem, namely, is it true that the best density is achieved by a blow-up of some finite graph, like for many other problems, or not? Or there is an infinite sequence of graphs which achieve the best density, or something absolutely different happens. So the point in the whole C4 problem eludes us. The whole essence eludes us still. So the idea would be, or was for us, to study something in between. For when we forbid when we count red triangles and blue triangles, Goodman's theorem tells us exactly the answer. When we want to count K4s in both colors, we have no idea. What if we count K3s in triangles in one color and the K4s only in just one color, not both? So we were led to the off-diagonal Ramsey multiplicity problem, and this is what I would like to introduce here. So the limit, the off-diagonal Ramsey multiplicity limit, is just that we are just minimizing the CST. This is a number and it exists, it's a limit. We are minimizing the S-independent set density and the T-clique density. And in particular for the 3-4 case, so the one in between Goodman's theorem and the K4 multiplicity, we succeed in determining the limit, which is this number. And we identify the unique stable example, which is this beautiful graph, which you can see on the picture, the Schläfli graph, on 27 vertices. It's 16 regular. And that's the unique example which achieves this limit, and this whole problem is perfectly Schläfli stable in the sense which I described earlier. So the Schläfli graph is a very nice graph. It comes up in many cases. It also is the graph when you have this, I think in algebraic geometry, you have these famous theorem that in cubic surfaces you have 27 lines, and then the Schläfli graph is there, or maybe their complement, or I don't remember. It is their incidence graph. So that the lines are the vertices, and if they intersect, then you have an edge. So this is a very beautiful symmetric graph, 16 regular, and this gives the extremal construction for this off-diagonal Ramsey multiplicity problem. We also managed to determine the off-diagonal Ramsey multiplicity when we have 3, 5, and this is also represents a case when we have a unique blow-up, which is better described as the complement of the Schläfli graph for the C5-3 problem, right? So the C5-3 is the same as the 3-5, and for that, the complement of the Schläfli is the unique extremal example. Here, we did not succeed with stability because the flag algebra gets too big. And for C4-5, there is a reasonable candidate, which is some graph which was found by search heuristic on 128 vertices, and it's a vertex sensitive graph. Again, lower bounds are with stability. Once you study the off-diagonal Ramsey multiplicity problem, it is natural to ask yourself, what is the full trade-off between independent sets and cliques? Namely, what can we say about the region of densities which can arise as a S-independent set density and a T-clique density? Okay, so this is the region of all XY pairs, such that there is a graph sequence with growing size, such that the S-independence densities tend to X, and the T independence density tends to Y. We define the little CSTX function as the infimum of all those y's where xy is in this region. So the big CSTX is the supremum of all these values. And one can show that this region of potential xy pairs, so these density pairs which can arise, is a nice set. So it is above every x, it is an interval. It's a closed interval. Furthermore, these curves, they are decreasing, continuous, and almost everywhere differential. So it's a decent, nice region. I would like to say that Liu, Mumbai, and Ryer before us, and actually this proof is based on their theorem, proved a similar statement about arbitrary quantum graphs, so linear combination of graphs instead of cliques in the case when S is 2. But here, crucially, our S is arbitrary. And here you can see some regions which we know. So when S is 2, and you have the clique on the other side, this is a very famous problem. This is the interplay between the clique and the edge density. And this was famously solved by Rasborov for t equals 3, for Nikiforov for t equals 4, and Ryer in general. And the lower half of this region is very intricate. These points, red points, represent the two-rank graphs with more and more parts, and in between, this curve is concave, and that was extremely difficult to show, and this is what Rasborov, Nikiforov, and Ryer succeeded to do, to describe that what is this concave function. In fact, inside it, it is still a tripartite graph, but it changes a little bit, and the proof was very difficult. The upper curve was determined precisely by Huang et al. And this looks very complicated. It is a consequence of the Kruskal-Katona theorem. So, because the extremal construction is just the clique and some extra stuff. So you try to concentrate into a huge clique as much as you can. For the case when S is equal to 2 and 3, and S is equal to T, and both of them are 3, the region is very simple. It is linear between. This is Goodman's theorem in between, and you can fill up this line completely. So one of these is the complete bipartite graph. The other one is the two disjoint cliques of size n over 2. And here, this is in the middle where these two curves intersect. So these regions are well understood in these small cases. Now here is a region, and this is what we found for S equals 3 and T equals 4, which is the next open case. As I said, the upper bounding function is known, and we try to get some information about what happens below. And here is the Schläfli graph, which was the extremal construction for the off-diagonal Ramsey problem when both the triangles and the T cliques appear with coefficient 1/2. And we try to establish some similarity with, say, the 2-3 graph. Okay, here you see the two-rank graphs as these points of non-differentiability, but we know that the function itself is continuous, but there are points of non-differentiable points, and in between concave curves. Now here, one can show with flag algebra that a slightly tilted line is still a lower bound on the whole function. So this means that this is a point of non-differentiability. Here you can see these constructions which were found by Nikiforov and Das et al. And Pikurko for the G4-3 and the G3-4 problem, right? When you forbid either independent sets of size 3 or cliques of size 4, right? The blow-up triangle and the blow-up C5. And now you can try and see whether there is anything in between in convex position. Well, we tried, and somewhat disappointingly, we succeeded. So there is something between this in convex position, and there is something between this and this also in convex position. And when you find a graph on 24 vertices, maybe you say, okay, now I'm going down to 20, Schläfli graph is 27, this is 24. But then you find another one on 40 vertices, which is in convex position from here to here. And the same disappointments on the other side. So here you can see a graph on 112 vertices and 128 vertices. So what we learned from this experimental study, that this region looks really complex. So I don't know what to think. We know that this curve is continuous. We know that it's almost everywhere differentiable. We know one point, which is a non-differentiability point, but then, yeah, I don't know. It will be complicated, but I think it's worth further investigation, definitely. Are there any questions?
Yes. Yeah, nice. Good.
Okay, so let me say a few words about how do we find the upper bound constructions. So, as I said, the origin of it is Thomasson's first counterexample from the 80s. He used blow-up of graphs. So I already said what is a blow-up. So this is a blow-up of this here is a blow-up of this small graph. And what's the advantage of the blow-up? The advantage of the blow-up that you can very economically count in it both the cliques and a bit more subtle, but also the independent sets. So there is a simple formula. Well, for the cliques, you can also immediately see that how to count the cliques. You have to take a clique in age, and for each clique in age, you can take m to the t from this blow-up. And for the independent set, this formula involves somehow the Stirling number, right? So independent sets you could also take like this, that you take them you find an independent set here like this, and then somehow distribute the t vertices between these three here. Yeah. So this is bringing in for you the Stirling number, where you partition into L parts. But anyway, the whole point in this little lemma is that there is a simple way that once you have an age, you will know what's the density of t cliques inside the blow-up. And this just depends on the calculation on the little h and nothing else. And also, you know that this tells you the density of t-independent set in your blow-up. Again, something which depends only on the little h and nothing else. So it's a finite calculation. And then once you have it, then you have just one task, right? Search for h, where this number is as small as possible. And this number, Thomasson called it sigma of h. If I divide this, if I compare it with the randomized density, so it means that if I find a graph with the sigma less than 1, then I have a counterexample with this sequence. And for our other problems where we are not looking at the symmetric Ramsey multiplicity, then we have a bit more general, right? So we have a maybe we are studying this curve, right? And then we are trying to find on the CST of X curve some new construction. Then maybe you want to count the independent sets with a different multiplicity coefficient, not 1. And for GST, when you actually forbid the independent sets of size t, no, you forbid the right, so this is actually incorrect, which I'm writing here, so this should be an S. Because I'm talking about the ST problem. So when you forbid right, so when you forbid the other way, doesn't matter. Right. Then what you forbid, when you forbid the independent sets, then you simply do it by making this mu very, very large. So your search automatically discards those graphs which do have independent sets of size t. What are the heuristic search methods we use? We have a discrete search space, which is just 0, 1 to the n, where this is a Boolean cube where we have a cost function. This is this function which I just saw here, which is measuring this critical number for each graph h, and we just want to find where this cost function is minimal on this whole search space. We have what search spaces are we using? Well, every search space will be a Boolean cube where we are searching for the minimization of this cost function. The simplest one is just that you take big N to be little n choose 2. And in this case, little n, big N corresponds to the number of edges, and your vector in your search space describes your graph on little n vertices. And this little n is roughly square root of 2n. Now, if you start looking at this, then you will experience that looking through all graphs is feasible when the number of vertices is 7. Generating all isomorphism classes is feasible up to 10. There are lists. Brendan McKay has lists of all graph isomorphism classes up to 10. If you are doing a bit more clever bounded search tree, searching for the best minimum, you can go number of vertices 15. And our experience is that any search heuristic will not be effective on this search space when n is more than 40. because simply you start any search, you will just not see so much of the tree in your lifetime that you will never see the interesting things. And in this problem, the C4 problem, right, the Thomason problem, the first counterexamples come up when the n is in the 30s. So Thomason, the smallest construction of Thomason, which was a counterexample, is 36. Adam Wagner found one with reinforcement learning with 34, and we found 33 with another method. So we need to do something else in order to improve here. So many of the previous constructions were Cayley graphs, though they never exploited this structure in their search. I will talk about what they exploited, but they never specifically looked for Cayley graphs. So you can take a look at the Cayley graph search space. So what is a Cayley graph? You have a group, you have a subset of this group, not the identity, such that it is symmetric, so it is its own inverse. Every pair of a group element and its inverse, either both are in or none. And then the Cayley graph is defined on the group such that the edges are those for which I get from one to the other by multiplying with an element of S. Now, for us to generate a Cayley graph, we took a vector where for every such pair, GG minus 1, which is a potential member of the generating set. And this way, the length of our vector is somewhere between G over 2 and G, right? So if in your group, everybody has order 2, then all of these guys have one element, so you have G minus 1, but maybe nobody has order 2, or not nobody, but most of them not. And then you have only G over 2. But it doesn't matter. It is much better because now with a vector of length n, you will generate graphs on n to 2n vertices, right? So this is much better than earlier when you just generated on square root 2n vertices. So going immediately for the generator gives you a huge advantage in how large graphs you can generate. And the problem, it is
how you choose the group, right? So now you have a lot of for the group.
Many groups are possible. I will speak about that a little bit. So it is certainly much larger graphs, and vertex transitivity helps with clique counting, because that's also a problem when you get into the hundreds. By the way, Benny, what is the end of my, when do I stop?
That's what I want to say. Maybe say 3-4 minutes.
4 minutes?
Yeah,
or,
some 4 minutes.
Okay, good. So we work with 3 different methods. 2 of them are very old: simulated annealing and taboo search. They are very simple local search techniques in searching exactly in, they are both from the 80s, searching in this discrete hypercube the minimum. And in simulated annealing, the point is that, of course, you can search and you go always to the neighboring vertex in your hypercube, and then you evaluate, and you always go to look at your neighbors and you change in a direction where you improve, right? But this way, when your function is absolutely unknown, you might get stuck in a local minimum, which is very far from the global. So the searches, simulated annealing and taboo search, in simulated annealing, there is a probabilistic, there is a chance that even you go to the direction which is verse. And this way you can get out of your hole. In taboo search, it's completely deterministic. You simply have the past best states in your head, and you are picking always the best state, but you are not allowed to kick out. This is the taboo, that you are not allowed to kick out some of those. You are not allowed to go back to one of those which you visited in the past L steps. So these are very, very simply programmable heuristics. And then there is a third method which we actually started trying out because you gotta do some machine learning nowadays. And this was an approach we followed. We started before, but we then followed what was suggested and successfully applied by Adam Wagner in reinforcement learning, where you feed this whole thing into a neural network and you use the cross entropy to calculate new distributions, and this is how you generate your examples. So these are the three methods we tried. And right, so there are libraries of small graphs you can also try, and this can be successful if your construction is not very big. But since time is getting up, I want to say what we found and how we worked. So for us, all three methods could improve the best known construction for C4. But what was very surprising, that the simplest among them, the taboo search, which is one line to program, gave us the best possible, graph which we have found on 768 vertices. And reinforcement learning also improved the earlier Thomasson construction, but it is much worse. Gave us a much worse result still than what we could find with taboo search. And on 192 vertices, we tried actually all groups. And on 192 vertices, reinforcement learning found its best one. And yeah, maybe here are some comments which I can close with. So reinforcement learning, right, so 192 all groups were tried. If you go a factor 2 above, you have no chance. On 192 vertices, reinforcement learning beat the best known bound, but taboo search, very stable, always finds a better one on the same number of vertices. And one observation is that the size matters in this problem. So how big your group is, how big your graph is, will give you a better chance for a better construction. But prime factorization for us was also important, namely having one factor of 3 instead of 2 factors of 2 seems really better. So here we really tested many groups, and 192 is much better, and 768 is also of this form. That was the highest we could go for. And right, so the groups we succeed in are all of this type. And the earlier construction mostly looked at groups where you have, or many of the early constructions, they looked at groups where you have just C2 to the end. And here are some anecdotal benchmarking, which also shows that for us, at least in this problem, taboo search was the winner. Okay, right, so I have other things to say, but maybe I will stop here and give it time for questions if there are some.
Perfect. So thank you, Tibor. Right. So let's thank Tibor. Thank you for a nice talk. So I ask a lot of questions. So if anybody else has questions, please unmute them yourself and ask. I see. So I guess, yeah, we ask lots of questions. Very interesting. So lots of open questions. So people who were at the talk are very welcome to try some.
May I show you the open questions, maybe? Is it okay?
Yeah.
Let me. Where is it? Here they are. So for large T, the answer is very much unknown. You can see.
Mm-hmm.
For large T, it's a constant from above. This is still Thomason, and this is David Conlon. And it's a constant to the T square from below. Rödl thinks that this ET should go to 0. Maybe he even thinks that it should go to 0 exponentially.
You mean you can beat, right, the best, the random by that much?
You can beat the random by that much.
Yes.
And right. And as I said, the nature of the Ramsey multiplicity of K4 is really a mystery. So all these off-diagonal ones, we found them to be blow-ups, but it's absolutely unclear what happens for K4. If it is that, it has to be really massive. So it has to be a huge construction. But maybe it's completely different. Understanding the best constructions, right? So we have a construction on 768 vertices. We don't understand it. It's a group, some set of generators. This is what Tabu search gave us. What is it? Generalize it for arbitrary T. There are really no constructions which work for any T and not just the same graph for us. So Thomason's construction is like that. It is a construction for any T. This is a construction for C4. Yeah. Right. And the question of the G's is also interesting. So here we found some new values, but there are many open ones. Okay, and then here is the advice that for your extremal needs, you have to give these good old optimization heuristics a chance.
Yes, yeah, I see. I see.
Okay.
Great. So thank you very much again. So last chance to ask questions. So if not, I think we can stop recording.